Hello, year 12s, back again. Just wanted to take a moment out of Hazy, chapter 2, page 46, just to review some of the elements of differentiating E. So we use a lot of the natural exponent in this investigation, and some of you might have not been familiar with how to differentiate E. So when we think about the differentiation rule, if we have a function, and if our function is simply e to any value, the derivative of that function remains e to that value. And when we have a function that constitutes e to another value or another function, when we find the derivative of it, we actually end up saying I've got that e to whatever that function is being multiplied by the derivative of that exponent. So you can see that when you've got this value, that function, this part of it is the same. And what often happens when we differentiate the function, if it's looking like e to a function, we end up having to multiply it out to simplify it. Now, when we look at our investigation, and that's just a little excerpt from Hazy, page 46, chapter 2, when we look at our integration of all the different parts of our investigation to date, we ended by talking about finding the second derivative so that we can locate our point of inflection. So we want the point of inflection, and when we found the derivative of our function, the function actually was quite a complex one, and we ended up last time with that situation where we could find the point of inflection. We can use our null factor to apply our point of inflection to find our x value, and we were looking to find our y coordinate of the point of inflection, and by doing the substitution of the x coordinate into the original function, we were able to find the y coordinate. And I did invite you to the Zoom session on Friday if you are unclear about how to do that. So at the end of the calculations, you're going to find that you have the coordinates of the point of inflection under the section of B, where they're asking us to, over here, to determine the coordinates of the stationary point and the point of inflection and to label these on the graph. Now, I know we haven't actually graphed them yet, but let's first finish all the calculation part, and I think you'll find the graphing quite enjoyable. What we need to lead into now is part C. So I might use a purple pen here. So if I take this little section here and I'm going to make it C. So now we are here where we are saying repeat the investigation for 3 different values of A while maintaining B at 4. Later on, they're going to ask us to repeat the investigation and make conjectures of keeping A constant and having different values of B. So we're going to try out both of them, but for right now, we are going to have the 3 different values of A and see the impact of changing it on our calculations, and later on we're going to include the graph that's going to summarize our findings and how that is different. So I'm going to just show you the possible changes that might happen if a potential A value is changed. Because I'm not the one working out the investigation, I'm not going to be showing you exactly all the possible values. I'm just choosing one for our purposes, and I'm going to say I'm going to choose A values that is going to be an A value that is going to be 6. So they had in the original sum an A value that was 10. So I'm going to now change it to an A value at 6, and as per instruction, keep the B value at 4. And we're going to essentially go through the same process of finding the stationary point and finding the point of inflection using exactly the procedure for finding the first derivative and later finding the second derivative. So when you've got your new f of x, so now we've got our f of x, our function looked like this, ax e to the power minus bx, and we've got our new a and our b, which is going to remain constant. When I substitute my value, where f is now going to be a value, I'm going to have a 6 instead, and I want to know what's going to happen to my function. I'm going to have 6x e to the power minus, and I still have my b, which is 4x. So I still have the same form, but a different a value. When I do my first derivative, which I need to find my stationary point, I'm going to again use the same product rule that I did earlier in one of the previous videos. Use the same product rule, and if you identify correctly that u is this time equal to 6x, then u dash is going to be 6. If you've identified v as e to the power minus 4x, then v dash is going to end up being e to the power minus 4x times the derivative of that f of x, which happens to be negative 4. And just like I said to you earlier on, when you simplify this derivative of e, you multiply it out and you end up with negative 4e to the power negative 4x. So that's what you've got, and that will end up being your u dash, your v dash. You substitute it into your product rule, and after multiple levels of calculation, I'm going to write the final answer that I found for my first derivative, 6e to the power minus 4x, 1 minus 4x. Now, in your investigation, you're not going to be using the value of 6 because I used it. So you're going to have to choose another value. But you should be able to see a pattern beginning to emerge. So what we want to find is that since 6e, this is this one here, since 6e is going to e to the power of negative 4x will never be equal to 0, the only option is for us to make 1 minus 4x equal to 0, and we eventually end up with an x value of a quarter. Okay, so we've got that because we cannot use the null factor because the e will always be greater than 0 if we substitute it into this part of the function. So we then go on to the next part, which is substituting. Remember, this was our original function, 6x e to the power negative 4x. We're going to then substitute our values and say, yep, I know what x value I've got, and so I'm going to say I've got 6. My x value is a quarter, and I've got e minus 4 times a quarter, and after my calculations, I ended up with that y coordinate. So if this was a quarter, let's backtrack there. I end up with my y coordinate being 3 over 2e. This is having multiplied it out. So I end up with, therefore, the coordinates of my stationary point when a is 6 ends up being x being a quarter and y being 3 over 2e. So that's my stationary point. What we found out from the last time was that if I calculate my second derivative, I'm in a good position then to identify my point of inflection and then also calculate, using my second derivative, the y-coordinate of the point of inflection that I found using the second derivative. So if I'm going to continue just with a being 6, I'm going to say this was my first derivative. So I already had that one, 6 e to the power negative 4x. 1 minus 4x, that was my first derivative. I already located that one over here when we had the beginning of how do I find my first derivative, which was over here. So I take my first derivative, I differentiate it again, because now I'm finding my second derivative. I'm going to use the same product rule at the risk of being laborious. Just a reminder that you can break your two functions down, and you've got u this time. I might just use a different color pen so you can see where we are. So I've got a u value, and the u value is e to the negative 4x, and then I've got my u dash value ends up being e to the negative 4x times minus 4, which translates into negative 4e minus 4x. So that's my u values, and then v is 1 minus 4x. And when I differentiate him, I end up with just negative 4. The reason for that, just like before, we would take our 6 out as a constant. So all you'd be left with actually differentiating, all you'd be left with differentiating would be the 6 which is on the outside and the rest of the function. So your function would essentially look like this. 6 with a wide open bracket, and you've got your negative 4e to the minus 4x times the component. So you're just applying your product rule, plus e to the minus 4x times minus 4. And once you work through all the different levels and the different steps, and you take out a highest common factor, you end up with a final answer for your second derivative being that. So we've got the same situation arising. You've got e in the first part and no e in the second part. This part is going to never be 0, always greater than. So at no point will you have a gradient that is 0. So that part can't be used with a null factor. You take the second part, which is 2 minus 4x. When is it equal to 0? And eventually you find out that x value is half. So if I substitute this value into my original function, I'm going to be able to find my y coordinate. Okay, so that's going to give me my y coordinate. I take my original function, which seems like a long distance away, which was over there, and my original function was 6x e to the power negative 4x. And I'm able to say, I now have an x value of a half. And I'm going to say that is going to get multiplied out. And when the whole situation's been punched into the calculator, you end up with a y value, which is 3 over e squared. So eventually our coordinates of the point of inflection is the x value of a half and the y value of 3 over e squared. I'm going to just highlight those 2 points because that's what we're essentially looking for every single time. We're looking for those 2 values which make up the component in our part C of the investigation of the changing A values. So what you're going to need to do is have those changing A values that's going to come up again and 3 more times. You need to show evidence that you can change this A value 3 times going through this entire procedure, and you would probably do one of these in the main body of your investigation and the other 2 values you're going to do in the appendix. Otherwise your investigation will be too thick. Okay, I will then see you at the next lesson.